Hi there. Last week we looked at differentiation of some common functions, and we also looked at the chain rule, the product rule and the quotient rule. This week we're going to be looking at some differentiation for some specific types of functions or equations. So let's get started with parametric differentiation. So first, what are parametric equations? Well, sometimes we can have equations where we have two variables, say x and y, and it can actually be easier to express these variables separately in terms of a third variable. So for example, here we have this equation, which is the equation of a circle, which is x squared plus y squared is equal to r squared. So r is the radius of a circle, so that's a constant. So this equation is basically for any point, let's say here, on a circle. So this would be the circle going around here, about this point, which would be the centre of the circle, the x here. Then we essentially have an x coordinate and a y coordinate for that point here. So we can express this coordinate, say x, as r cos theta from SOHCAHTOA. So theta is the angle of rotation, the angle that that point is sitting at relative to the horizontal. So that becomes our third variable. Similarly, we can express y as r sine theta. So we now have these two variables, x and y, and we have a third variable, which is theta. Okay, so we can then find an expression for example, dy by dx, so the differential of y with respect to x. So let's take a look at how we do that. So for parametric equations, a differential like dy by dx, the differential of y with respect to x, would be equal to the differential of y with respect to the third variable theta here, and that's all divided by the differential of x with respect to the third variable theta as well. So depending on the problem that you're looking at, the third variable could be something else. It could be, for example, t for time. In this case we have an angle theta. Now looking at the second differential, so how do we find the second differential of dy by dx? So here we can see that we have dy by dx and we differentiate that with respect to the third variable, so in this case theta. This is then all divided by the differential of x with respect to the third variable theta. Okay, so let's take a look at an example. So let's say we have this equation of a circle where we have now x is equal to r, the radius, multiplied by cos theta, and y is equal to the radius multiplied by sine theta. So if we are asked to find y by dx, the first thing that we have to do is differentiate each of these x and y in terms of the third variable theta. So the x by the theta, differentiating x with respect to theta, gives us minus r sine theta. Hopefully you remember that the differential of cos is negative sine. And then the differential of y with respect to theta is equal to r cos theta. Again, hopefully you remember that the differential of sine theta is just cos theta. Okay, so now to find dy by dx, we do the differential of y with respect to theta, which is r cos theta, all divided by the differential of x with respect to theta, which is minus r sine theta. So then these r's cancel off and you're left with minus cos theta over sine theta. We can also say that that is equal to minus cot theta, the cotan of theta. Okay, so that is our differential of y with respect to x for that problem. So now what if we were asked to find the second differential of y with respect to x, and so to 2y by x squared. So to 2y by the x squared is just equal to the differential of the y by the x with respect to the third variable theta. So from the last slide we can see that the y by the x is equal to minus cos theta over sine theta, and we can then use the quotient rule to differentiate that, and that's all divided by the x by the theta, which is minus r sine theta. So the first thing that we should do is to differentiate the top line using the quotient rule. So we can say that u is equal to minus cos theta and v is equal to sine theta. So that means that du by the theta is equal to, well, differential of minus cos theta is just sine theta, and the differential of v with respect to theta is just cos theta. So using the quotient rule, we can say that we have v, which is sine theta, multiplied by du by theta, which is also sine theta, minus from that u, which is minus cos theta, multiplied by dv by the theta, which is cos theta, and then that's all divided by v squared, which is sine theta, all squared. And then to add to this, we have from here we have minus r sine theta from the bottom line of the 2y by the x squared. So we can then say, hopefully you'll recognise that on the top line here we have essentially sine squared plus cos squared. So that actually goes all to 1. Hopefully you remember that as a trig identity. So on the top line we just have 1. And the bottom line we have minus r, and then we have sine squared theta times by sine theta, which gives us sine cubed theta. Okay, so that's us obtained an expression for the 2y by the x squared for that example. So next we're going to look at differentiating implicit functions. So what are implicit functions? Well, there's a couple of examples shown here where we have y to the power of 4 plus 2x cubed, and that's equal to 5y squared minus x. So essentially what happens here is that we can't write y equals blah 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 in terms of x. Similarly for cos y is equal to 3x squared plus 4xy, we can't simply write y is equal to blah 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 in terms of x. That would be, if we could do that, would be an explicit function, and so because we can't do that, these are implicit functions. Okay, so to differentiate implicit functions, essentially for any of these problems, if we were asked to find the y by the x, we actually have to use the chain rule. So for the chain rule, you can remember that the differential of a function f with respect to x could be equal to the differential of that function with respect to y multiplied by the y by the x. Okay, so to see what I mean, let's take a look at an example. So here we have a function which is f is equal to 5 times y to the power of 6. We're asked to differentiate that function f with respect to x. So that might seem a little bit strange because there's no actual x appearing in this side of the function. However, we still can find an expression for the f by the x if we use the chain rule. So from the chain rule we have the f by the x is equal to, we have first the f by the y, so we differentiate 5y to the power of 6 with respect to y, and then that's just multiplied by the y by the x. So we don't have an expression that tells us how y and x are related, so we can just say the y by the x. So we can now just differentiate this function here in terms of y, and that gives us 30y to the power of 5, and then that's just multiplied by the y by the x. And that's actually just our final answer for that example. So let's now take a look at a more complex example of implicit differentiation. So here we have 4x cubed plus 2y squared minus 6x plus 3y is equal to 4. And we're asked to find the y by the x. So how can we actually find the y by the x? Well, what we have to do is essentially differentiate each individual term with respect to x. So if we differentiate the first term with respect to x, so we have 4x cubed, that would just go to 12x squared, as it normally would. Next we have 2y squared. So here we have to use the chain rule to differentiate this with respect to x. So first we differentiate it with respect to y, so it becomes 4y, that's then multiplied by the y by the x. The next term, minus 6x, we can differentiate that with respect to x, and it just becomes minus 6. Then we have plus 3y. So again, we differentiate it with respect to y, which would just give us 3, and then that's just multiplied by the y by the x, according to the chain rule. And then we have, on the other side, on the right hand side, we have just 4, so if we differentiate that with respect to x, we just get 0. So we can now essentially collect terms to find an expression for the y by the x. So we have 4y plus 3 is all multiplied by the y by the x. And that is equal to, if we take the other terms to the other side, we have 6 minus 12x squared. So we can then say that the y by the x is equal to 6 minus 12x squared divided through by 4y plus 3. And that's our final answer for the y by the x for that implicit function. So following on from implicit differentiation, I now want to take a look at logarithmic differentiation. So we really look at logarithmic differentiation where we have x up in some power. So x is somewhere in the power of a term. And that means that we can't use the sort of standard rules of differentiation, and we have to do something different. So what we actually have to do for logarithmic differentiation is use the log laws and also use implicit differentiation. So let's take a look at this example here where we have y is equal to a to the power of x. So a is just some arbitrary number, it could be anything. So the first thing that we need to do before we differentiate this is get it into a form where x is no longer a power, or it's no longer part of the power. So what we have to do is take natural logs of both sides of this equation. So that means that we have natural log of y is equal to the natural log of a to the power of x. And hopefully you'll remember then from the log laws that we can write that the log of y is then equal to x times the natural log of a. That means that we now have x is no longer a power. We have it in sort of down there as a coefficient, so we can now look at differentiating this function. we are looking to differentiate y with respect to x, find y by x, so we do need to use implicit differentiation here. So if we use implicit differentiation for the left hand side, then we're essentially first differentiating the log of y with respect to y, which gives us 1 over y, and that's multiplied by the y by x according to the chain rule. Then on the right hand side, we're going to essentially differentiate the right hand side with respect to x, but log a, natural log of a, will just be some arbitrary number, okay, so it can be considered a constant. So that means if we differentiate that with respect to x, then we just have the natural log of a. So that means that we can write that the y by the x is then equal to y times the natural log of a. Okay, and then our last step is to substitute in the actual term for y into this equation. So the y by the x is equal to a to the x times the natural log of a. And that is the equation, or the expression for the y by the x for that problem. So to make sure that that's clear, let's take a look at an example with a numerical value of a. So let's say that y is equal to 5 to the power of x. Then if we want to differentiate that to find the y by the x, the first thing that we have to do is take the natural logs of both sides. So we have the natural log of y is equal to the natural log of 5 to the power of x. Using the laws of logs, you can say that the natural log of y is equal to x multiplied by the natural log of 5. Okay, so we then want to differentiate this with respect to x, so using implicit differentiation on the left hand side, that we can say that differential of the natural log of y with respect to x is 1 over y times by the y by the x. That's then all equal to the differential of x times log of 5, natural log of 5, which just gives us the natural log of 5. So the y by the x is then equal to y multiplied by the natural log of 5. And our last step, we cannot forget this step, is to put in 5 to the power of x in place of y, and we have the y by the x is equal to 5 to the power of x multiplied by the natural log of 5. So now the last type of differentiation that we're going to look at is partial differentiation. So partial differentiation can be used where we have a function, say z, is equal to some function of x and y. So x and y are two separate variables, and so we can partially differentiate z with respect to one of these variables. So to see what I mean here, let's take a look at an example where we have z is equal to 4x squared plus 3x to the power of 4 times by y squared minus 3y cubed. So if we want to partially differentiate z with respect to one of the variables, say x, then what we have to do is differentiate z, each term of z, with respect to x, but now we treat the other variable y as a constant, so we don't differentiate y with respect to x as we would for implicit differentiation, where we would use the chain rule to do that. So we don't need to do that for partial differentiation, we just treat the other variable, which is y, here as a constant. So let's say we want to find the partial differential of z with respect to x. Note here that partial differentials are usually represented by curly d's. instead of the standard d's. So first, if we differentiate 4x squared with respect to x, we just get 8x. And then if we differentiate the second term with respect to x, then we get 12x cubed multiplied by y squared. So as I said, we just keep the y as a constant. We treat it as a constant, just some arbitrary number. And then finally, if we differentiate the last term, which is minus 3y cubed with respect to x, then we're just differentiating a constant essentially with respect to x, so that just goes to 0. So our expression for the partial differential of z with respect to x is 8x plus 12x cubed times by y squared. What if we want to find the partial differential of z with respect to y? Well, essentially we're going to do the opposite. We're going to differentiate z, but now we're going to keep x as a constant. So if we differentiate the first term with respect to y, we treat x as a constant, so the first term goes to 0. The second term, we have now the 3 is multiplied by 2 to give us 6. The x to the power of 4 just stays where it is, and the y squared goes to y. And we can then differentiate the last term, which is 3y cubed, which if we differentiate with respect to y gives us 9y squared. And that is our expression for the differential, the partial differential of z with respect to y. So partial differentiation is almost easier than implicit differentiation because we just treat the other variable as a constant. So just try not to get muddled between implicit differentiation and partial differentiation, and think about what the question is asking you to find. So in this video we've had a look at parametric differentiation, implicit differentiation, logarithmic differentiation, which uses implicit differentiation, and finally we looked at partial differentiation. So thank you very much for watching.